Okay, our next speaker is Bao Vuong. He will speak about fundamental group and twisted Alexander polynomial of link complement in 3 torus. Please.
Okay, thank you. I will speak in English because for me, my lesson may be even harder. So, as we know that the knot theory is now a vast subject that come across every field of mathematics. So one of the directions that extends the knot theory to the different direction is in the classical case, we consider the circle, the embedding of circle in the three-dimensional sphere. And there several now has been done for the embedding of the circles in the different three-dimensional manifold, like in the length space, the dodecahedral space, and the virtual knot theory is the embedding of circles in thickened surfaces. And I happen to read the work by Cattabriga, some Italian mathematics in the that work on the knot theory for length space. And I have done something to the similar direction when I consider the manifold that the circles embedding into is a three-dimensional torus. And I carry on the work similar to Cattabriga in the length space to the three-dimensional torus. And when I had this done, and I found that there's some work in three-dimensional torus, the embedding of the circle in the three-dimensional torus have done priori me. That is a work by Dechery and Hoff and Dapkowski and Maskowski. That's embedding of the circles in the oriented surfaces crossed with the circle. Because in the case of three-dimensional torus, it is that the torus, the two-dimensional torus, cross the circle or cross product of three circles. Okay. And then we consider the three-dimensional torus as the CW complex as the identification of the cube. And we have the three-dimensional torus as the identify of the opposite faces of the cube. And we have the model for three-dimensional torus. As it is so in the picture, we have the three-dimensional torus as along with the cube. And I will denote that the math, the Gaussian math from the cube to the three-dimensional torus is EF, because when we embedding to the circles to, I mean, the disjoint invariant circle is a link to the three-dimensional torus when we embed in the cube, and after that we Gaussian space of the embedding circle to the cube here. Yes, and when I use diagrammatic or the combinatory absorb to this consideration, and when you embed to a circle into the cube, we define some certain condition so that the embedding will consider to be nice, because when we consider the cube, it is CW space that it will be give some confusing if we not consider in the general configuration of the the curve that's in embedding in the GIF. So we restrict to the case that the link in the GIF have not to intersect with the vertices, not intersect with the axis, and the curve in the GIF are not tangent to the face of the GIF. And this will be considered to be the regular embedding. And then when we have the embedding, we would like to consider some combinatorial like diagram. And for that, we have to find a projection of the curve to some plane. And then we get the diagram. In the case of the three-dimensional torus, it's different from the case of the three-dimensional sphere, that every node and link is finite in the three-dimensional sphere, so that it's local. So when you project it into some plane, there's some specific point of view that you project it, and it will look at the node or the link like as a whole, but there are no such specific point in three-dimensional torus, because there nowhere you can look at the node as a whole. So when you choose a point to project the node to some plane in three-dimensional torus, it will cause some ambiguity that you have to specify in the further to make it well defined. And what is a regular projection? That projection has no cast, and the projection is transversal. The set of multi-points is finite, and all of them are actually double points. It is standard approach to the diagrammatic node theory. And no double point in the edges of the bottom face A, because I chose projection that it is a regular projection into some into a face of the GIF. And yes, and by doing so, we forget some certain information of the node when it's come over across the S1 circle of the torus, because we consider the two-dimensional torus crossed with S1 with a circle, and we project it along the circle, and it will cause the information that when it come along the S1 of the three-dimensional torus. And to define that, we had to add some extra structure on the diagram, the projection of the node. Namely, it is a dot that I will denote that the dot occurred in the projection when the node come along the S1 circle in the structure of three-dimensional torus. And we add some condition for regularity of the projection is no vertex at the crossing point too. So what we have in the picture, it shows that some embedding of circles in the GIF, and it's embedding of circle in the three-dimensional torus. The point here, the vertex that's with plus and minus signs is when it come over to the upper face and the bottom faces of the GIF, and it's been denoted by a vertex with negative and positive size. And then we get some diagram look like inside a square. That's so in the picture, I think it's clear what we get, or what we get after the projection. So it is that ordinary knot diagram in square with identifying the edges of the square. But we have now something more like two valent vertices. It's compared to only four valent vertices of ordinary knot diagram. Okay, and we have the radiometer moves and vertex move for this combinatorial model. For the radiometer moves, it is similar as Professor Sophia talked today in the morning. She considered some radiometer moves. That is when it's the across, so the move that the crossing and the curves has been moving via isotropy of surface across the considering fundamental domain of the periodic pattern that she considered. And it is a similar way. It's the same as that structure. When I had this thing done, I noticed that someone had come up with it before me too. So it's not something very, very new. And we had the vertex move, that's the wind moving across the crossing of knot diagram. And we can cancel out the two vertices if there's some condition to comparable of the vertices that has the same size, it's the same side of the when it's lie on the same arc. And we can switching vertex move that when we moving the vertex over crossing, it changes the type crossing. And a forbidden move that with forbidden when the size of the vertex has not it's not fit in the crossing. For example, in the lowest picture, when the size of the vertex has minus and it's the overcrossing, so we can't move the vertex over that crossing. Okay, it's just formalization of the projection. It's not nothing to do with it. And the theorem says that the two knots that embedding in the three-dimensional torus had to be the same if we can join the two diagrams of the linked by the radiometer moves and the vertex move. And as usual, we come up with the fundamental group of the common elements of links in three-dimensional space, and in this case, three-dimensional torus, and how to get a presentation of the fundamental group when we have a diagram of notch and link in three-dimensional torus. Okay, as usual, we assign arches of diagrams with letter, and it will be the generator of fundamental group. But in the case of three-dimensional torus, and we use this combinatorial model, it creates some ambiguity that the assignment of arcs in this type of diagram will not be well defined, because it's covered by the vertex. We have several vertex in this diagram, and depend of the configuration of the vertex when it's in the topological meaning, it's when the curve of embedding come along the S1 component of the three-dimensional torus. And as before, we don't have any point of view that it will be specific point that will look to the not like a local. In this case, there are no that local point. And then we have to kill that ambiguity that for some, when we get a diagram of notch in three-dimensional torus, we have to arrange it so that the ambiguity we get from the configuration of the vertices. So we have to do something with it. And what we do? First, we get the first picture. It's just arbitrary diagram. And then we arrange every vertices over via the vertex move and the randomizer moves, and we can arrange every vertices of with both with size negative and positive in unique domain unique region that vertex lies on unique region of the diagram considered as a graph. In this picture, I just arrange every vertices in the region A. That is this yellow dot, and we arrange it in one logger space, say in the square diagram, and then by doing so, we can specify every assignment of arcs in this diagram with unique element. That's going to be the generator of fundamental group of complement of link in three-dimensional torus. And then when we have the well-defining generator, the remaining things is not very hard to do, just using the Seifert Van Kampen theorem and as a Vertinger representation, we get a representation of the fundamental group of complements linked in three-dimensional torus, and we have certain more than that Vertinger relation, because we assign every us, and with generator we have relation between us when it come up to a crossing like vertical representation, and we have when two arcs, two aside of the arcs that crossing the boundary square of the diagram, and when it come to the vertex, and then we have the relation that due to the crossing, due to the vertex, and due to the intersection of the arcs with the boundary. And thus we have three types of relation: W, Q, and T. W, that's a Vertinger, ordinary Vertinger relation, and Q is when the arcs intersect with the boundary, and the torus relation is come from the torus nature of the embedding, because we embed in the three-dimensional torus, and thus we get a presentation of fundamental group. And if we embed some nodes and links in three-dimensional torus, we have the homology type of the knots that at a curve in three-dimensional torus, and we can define it easily from the diagram. Okay. And then when we have a presentation of fundamental group, we can get the Alexander polynomial of the space, complement space in the so there are many approaches to compute the Alexander polynomial of notch and length, and one of them is using the Fox calculus. And when we have a presentation of the group, we can get it. I don't want to. We can get this sequence of math that's using Fox calculus, and after some mapping, we get a matrix, and the Alexander polynomial will be the first elementary of the ideal that generates the first elementary ideal of the matrix. And in this similar way, when we have a presentation, we can compute, we have an algorithm to get the Alexander polynomial of the space that associates with the fundamental group. And for the case in the three-dimensional torus, not ending in this space, we get that the fundamental group, the homology group of that has the torsion pairs, and then we get not only Alexander polynomial, but we get the twist Alexander polynomial that sending the torsion pairs of the fundamental and homology group to some field. So let's say it's a complex field, and then we get that after that sequence of maps using Fox calculus, and we get the twist Alexander polynomial for link complement in the three-dimensional torus. When we get, we already have a presentation of the fundamental group. And then we can prove some theorem that's, okay, a log link in the three-dimensional torus, it's like inside some bond in the three-dimensional torus. And in that case, the twist Alexander polynomial will equal to 0. And we had the Alexander, to twist Alexander polynomial of the link. That is connected sum of and 1 and 2. That's one of them is a log link. So we had the Alexander polynomial is the product of the two Alexander polynomial that is the components of connected sum. And yes, and in the complement of the link in the three-dimensional torus, as usual, we can consider that it is a CW structure and its homotopy, simple homotopy to a two-dimensional CW complex. And this two-dimensional CW complex has the radiometric torsion the same as the complement of the link in three-dimensional torus. And as in the work by Minor, when he proved the duality, that he proved give another proof for the symmetry of Alexander polynomial, and using that same type, we proved that the radiometric torsion of link complement in three-dimensional torus is the same as the twisted Alexander polynomial. Okay, I'm stop here, and it's some reference for the work. Thank you.
Thanks.
Is it possible to consider maybe some double points on the face A?
Double point. in the
Double
face
points
A.
on the face A. You can use face A and haven't double points. And you can consider the case when maybe some double points.
I'm sorry, I didn't get the question. You
Ah.
can ask it in Russian.
Шестой слайд. Мало.
Шестой. Это?
Вот ты пишешь, что нет двойных точек на ребрах грани А. А если рассмотреть, что там есть несколько двойных точек, то что будет?
Ничего не будет. Это будет просто потом, что невозможно, чтобы определить какой-то ас, потому что если double point там, то есть мы не можем так определить, что это будет overcrossing or undercrossing.
То есть это определение уже такое.
It's just we specify. For us, it's going to be regular.
Еще вопросы? Тогда давайте поблагодарим докладчика еще раз и
Thank you.
кофе-брейк.